Welcome chemistry students to the next segment on covalent bonding. This is the fourth video in our series, and in this session we are going to talk to you about valence shell electron pair repulsion.
This valence shell electron pair repulsion theory, or VSEPR, or VESPR, if you don't want to say that word jumble there, it tells us why molecules have their particular three-dimensional shape. And what happens is there's a repulsion between the electron pair forces in the bonded pairs and in the unbonded pairs. We know electrons have different charges, and those negative charges want to repel against the other ones. And what happens is they want to move as far away from each other as possible. Now, in an unshared pair, they're not restricted by any of attraction from the two nuclei of a bond, nor is there any overlapping in their orbitals, since they're unshared and no bond is happening. So they will physically take up more space and give more of that repulsive force against any of the nearby shared pairs in the area. More space.
So here in this diagram, some of you may actually recognize from your textbook, is two triatomic molecules. You have carbon dioxide and water, and they have shaded in the unshared pairs of electrons on the oxygen molecule, and they even sort of shaded the shape of those orbitals as actually occupying more space. So they squeeze against the bonded pairs, the shared pairs of electrons, and instead of being as far apart from each other as possible, they are closer than that. And you get a bent molecule. In carbon dioxide, you'll notice that on carbon, there are no unshared pairs of electrons to squeeze those bonds any closer than they already are, so you end up with a 180-degree bond angle, creating a linear molecule. In these next couple pairs of atoms, you have methane, where again you have carbon in the middle with no unshared pairs and 4 shared pairs. Those 4 shared pairs are all exactly the same, and they're going to push against each other with the same amount of force and get away to their neutral corners and create a tetrahedral shape. In ammonia, you have the unshared pair on the nitrogen on that central atom, and it squeezes those bonds down and makes a pyramidal shape.
Okay, and again, the bonded atoms between, say, nitrogen and hydrogen here, that bond is representing some overlap. So even though the ball and stick model kit doesn't make it look like that, they're actually taking up less space, the bonded pairs, than those unshared pairs are.
Here we have common shapes that we may encounter, and again, this is another figure from your book that you may have been using while you work through your covalent molecule labs.
Page 233.
Thank you, Mr. Sustin. And you'll notice some of them are the familiar ones we've been working with. The big 4 ones that we talk about are linear shape, are bent, are pyramidal, and also the tetrahedral. We may encounter along the line some of these other ones, like the trigonal bipyramidal and the octahedral, as we work through different molecules, but those other 4 big ones that I just mentioned are the ones that will be definitely on your test.
Right, and you'll probably come across that trigonal planar molecule because that shows up a lot in the polyatomic ions, like the carbonate ion, where you need to have 1 double bond in there and then 2 single bonds and a little bit of hybridization, which we'll get to later on. So you do see that trigonal planar shape, and if you look closely at this diagram and start counting, you'll realize that some of those central atoms have more than 8 valence electrons, and there are some atoms that can do that. Sulfur and phosphorus can actually be happy with more than 8 valence electrons, just like our boron could be happy with fewer.
Especially when they combine with something that's dramatically more electronegative.
Right.
Right. So going back again to these shapes of molecules, you can either build them with the Tinker Toy molecular model kits, or you can pay very close attention to how you draw your Lewis structures. And this looks like a great opportunity to make up some flashcards, quiz yourself. If you have a molecule with two shared pairs of electrons on a central atom and no unshared pairs, you're going to end up with our friend carbon dioxide, linear. The double bond counts as one shared pair of electrons. It's a bond. If you have two shared and two unshared, as you do in the water molecule, and if you draw the Lewis dot structure, you'll see that for sure, it's bent. And three shared, one unshared, draw the Lewis dot structure for ammonia, NH3, and you'll see it's pyramidal. And with four shared pairs of electrons on that central atom and no unshared pairs on the central atom, those bonds are going to get as far apart from each other and make a tetrahedral molecule.
Now, this slide triggered a thought in that this is a nice little tally, and I remember there being a short answer test question where we asked the students to draw a couple Lewis structures and then tell us how many shared pairs and how many unshared pairs there are. And you got to read that question carefully and see if we're asking for shared and unshared pairs on the center atom or on all of the atoms, because those satellite, those outlying atoms, the, say, chlorine attached to a central carbon or something, that atom has unshared pairs as well. So yeah, that would be part of the tally, making sure that everything follows the octet rule. But spend a little time looking at your examples with that in mind and making sure that you can count up correctly how many are shared and how many are unshared.
We can also determine from the shape how it's going to affect our molecular polarity. So we've been dealing a little bit with polarity of bonds, and we did a video of that already. But when we talk about molecular polarity, we're talking about the whole molecule and what's going on with it, not necessarily just one bond. So as you can see in the example here, we've got carbon with two oxygens bonded to it. And even though each of those carbon-oxygen bonds has a polar bond, those two polar bonds are pulling in opposite directions, and in turn it's making that whole thing non-polar.
Each end of the molecule is exactly the same. The oxygen on the left end is a little bit negative. The oxygen on the right end is a little bit negative, and so each end of the molecule is exactly the same, nonpolar.
And you'd see that with something like methane as well, where each of those carbon-hydrogen bonds is polar, but overall it's fine, it's nonpolar. Thank you for watching. Make sure that you respond to the video homework, either in the Moodle Journal or the Moodle message, with a 3 to 5 sentence summary and a question that you have about this content, and we'll see you in the next video.